Welcome to the first video on triple integrals and volume. We can determine the volume of a solid region V by using a triple integral over the region V integrated with respect to V, which means if we let the integrand equal the most basic function f of x, y, z equals 1 and rewrite differential V as dx, dy, dz or some other order of these three differentials, and then let the limits of integration represent the solid V, this will give us the volume of the solid. And this is very similar to how we used a double integral to determine area. We can now use a triple integral to determine volume. And then remember, because there are three differentials, there are 6 possible orders of integration. In the intro video for triple integrals, we looked at this definition to evaluate triple integrals. We're going to use the same principle to determine volume, but f of x, y, z will equal 1. Let's take a look at an example. Here we want to determine the volume of a solid bounded by y equals negative 2x plus 4, z equals 3, with x, y, and z greater than or equal to 0. So the most challenging part about determining this triple integral is going to be determine the limits of integration with respect to x, y, and z. And to do that, it's often helpful to first take a look at the xy trace, xz trace, and yz trace. And this example is pretty straightforward. The xy trace would be when z is equal to 0. So we'd have the equation y equals negative 2x plus 4. So we'd have a y-intercept of 4 and a slope of negative 2. So we go down 2, right 1. And we also know that x is greater than or equal to 0 and y is also greater than or equal to 0. So the xy trace would be this two-dimensional region here. Now let's take a look at the xz trace. If we let this equal the z-axis and this equal the x-axis, we'll go through each equation and let y equal 0. This first equation here, if y is equal to 0, we could solve this for x. X should be equal to 2. That would be this vertical line here. Z equals 3 would be here. And again, because y and z are positive, this would be the region in the xz plane. And then for the yz trace, if we let this equal the z-axis and this equal the y-axis, if x is 0, we would have y equals 4. That would be this line here. Again, this is the y-axis. Z is equal to 3. And again, both y and z are positive. This would be the area of the yz trace. And these will help us determine the limits of integration. But next we need to decide in which order we want to integrate. Remember, if we integrate first with respect to y, the limits of integration must be in terms of x and z. And since this equation here is already solved for y, we'll start with differential y. And the order of the remaining two don't really matter. Let's go ahead and write this as dx dz. So the interval for y will be from 0 all the way to this line, which is negative 2x plus 4. And then for x, we'll go from 0 all the way to 2. And then lastly, for z, we can look at either of these two traces. Z will be from 0 all the way to 3. These intervals for y, x, and z form the region V, and therefore will give us the volume of the solid. If we take a look at V in 3 dimensions, the volume that we're determining will be the volume of this triangular prism here. So let's go ahead and determine this volume. We'll first integrate with respect to y. Now we'll evaluate this at the limits of integration. So we'll have negative 2x plus 4 minus 0. And now we'll go ahead and integrate with respect to x. We'll go ahead and do that on the next slide. So we'll have negative 2 times x squared over 2. That'll be negative x squared plus 4x. And then when x is 2, we're going to have negative 4 plus 8. That'll be 4. And then when x is 0, they'll both be 0. And now we'll integrate with respect to z. We'll have 4z. So we'll have 4 times 3, 0. That'll give us 12 cubic units. Let's go back and take a look at that region in 3D. This distance here was 2, this distance here was 4, and the height was 3. So if we had a rectangular prism, it would have length times width times height, or 2 times 4 times 3, that would give us 24. And we can see geometrically that the volume that we wanted was half of that. 24 divided by 2 would be 12 cubic units. Now most of the problems we look at, we won't be able to use one of our basic geometric formulas, but we could have on this one. And this does verify your answer. Let's go and take a look at another one that's a little bit more involved. We want to determine the volume bounded by these three equations. Let's go and take a look at our traces. Let's start with the xy trace. So we'll set z equal to 0. Notice if z is equal to 0 here, we'd have y equals 0. That would be this line here. Here we have the graph of y equals 1 minus x squared. That would be a parabola that opens down, shifted up 1 unit. So it would look something like this. So the bounded region in the xy plane is this region here. So this was y equals 0, and this was y equals 1 minus x squared. Let's look at the xz trace now. So we'll call this z, and we'll call this x. So y would be equal to 0. If y is 0, we have z equals 0. Be this line here. If y is 0 here, we'd have, if y was equal to 0 here, we could add x squared to both sides. We'd have x squared equals 1, so x is equal to plus or minus 1. So we'd have this vertical line here, and this vertical line here. And then lastly, for the yz trace, we set x equal to 0. So we have the line z equals y. That would be this line here, slope of 1. If x equals 0 here, we'd have y equals 1. This is the y-axis here, so it would look like this. And again, z is equal to 0, so we'd have this line here. So we have this triangular region in the yz plane. So our volume will be equal to the triplet integral over the region v with respect to v. So now we need to determine the order of integration as well as the limits of integration. This time I think we'll start with integrating with respect to v, y, and then x. So for the limits of integration with respect to z, it must be expressed in terms of y or x. So let's look at the yz trace. Z is bounded by 0, and this line z equals y. So it'll be from 0 to y. And then for the limits of integration with respect to y, let's go and take a look at this first trace. Y is bounded by 0 and this curve, which is 1 minus x squared. So it'll be from 0 to 1 minus x squared. Then lastly for x will be from negative 1 to positive 1 as we see here, as well as what we see here. And this triple integral will give us the volume of the solid. Let's go and take a look at that solid. So the volume that we're determining is this region in here, and as we angle this, you can see each of the traces. Let's go ahead and find that volume. Let's go ahead and start this on the next slide. So we're going to go with respect to z first. So we'll place z with y, that'll give us y, and then with 0, so we'll just have y. And now we'll integrate with respect to y. So we'll have y squared over 2, or 1/2 y squared. When we replace y with 1 minus x squared, we have to square this or FOIL it. So we're going to have 1/2, and then we'll have times 1 minus 2 x squared plus x to the 4th. And now we'll integrate with respect to x. We'll have x minus 2 times x to the 3rd over 3 plus x to the 5th over 5. So we'll have 1/2 times x minus 2/3 x cubed plus 1/5 x to the 5th. Let's go ahead and finish this on the next slide. X is equal to 1, we'll have 1 minus 2/3, that's 1/3 plus 1/5. 1/3 plus 1/5 will give us 18/15. And then when x is negative 1, we're going to have negative 1 plus 2/3, that'll be negative 1/3 plus a negative 1/5, that'll be negative 8/15. So we have 1/2 times, this will be 16/15. So we'll have 16/30, which simplifies to 8/15. And again, this gives us the volume of region V. So 8/15 is the volume of this solid region here, bounded by this green plane and this blue plane and this gray surface. We'll take a look at some additional examples in part 2.